next with us is Mick West. Many of you know Mick West. Mick West is the author of Escaping the Rabbit Hole, How to Debunk Conspiracy Theories Using Facts, Logic, and Respect. A retired software engineer, he is the creator of the site Metabunk, which utilizes crowdsourcing and technical analysis to investigate UAP cases. Mick uses his background in coding 3D graphics, physics, and linear algebra, honed by decades in the video game industry, to create custom tools with which to recreate, simulate, visualize, and analyze various UAP videos. Many of Mick's results are published on metabunk.org and at YouTube, at his YouTube channel as well. We're delighted to welcome Mick West, please.
Thank you very much, Michael. Thank you for that introduction. And I'm just going to share my screen real quick. Okie dokie. So here is my talk, and I apologize for the long title. I'll try to make it as interesting and as accessible as possible. And let's get right into it. What is a line of sight? In 3 dimensions, a line of sight is a line that connects your eye or your camera to a point in the world. In 2 dimensions, a line of sight is a point on an image, because your eye or your camera is always at one end of a line of sight. So if you're looking out at something, you can't actually see the lines of sight because they're all emanating from your eye or your camera. But if you were to kind of imagine it looking from the side, you can kind of visualize all these lines kind of shooting out from the camera to points in the scene. This connection between 3D lines of sight and 2D lines of sight is illustrated by this 1525 woodcut, which is kind of a manual camera. The focal point of this manual camera is on the wall on the right, and the line of sight here is this string. This assistant here is moving the line of sight to points on this object, and then the artist is going to plot a 2-dimensional point on the image focal plane, which is right here. So each 3-dimensional line of sight corresponds to a 2D dot on the image. And why do we use lines of sight in UAP investigations? Well, it's a very kind of fundamental thing in UAP investigations. Most UAP data we have is 2-dimensional. We have photos or we have videos which only show you a 2-dimensional view of the scene. But what we really want is 3-dimensional data. And the reason we want 3-dimensional data is that we're looking for anomalies. We're looking for unidentified anomalous phenomena. We're looking for the black swan that was talked about earlier, something that is different from the norm. And to do that, we need to figure out things in 3 dimensions. We need to figure out how big the UAP is and how far away it is. And that gives us how fast it's moving. And the velocity and the acceleration are the things that will actually show whether something is anomalous. Like you've just heard about the JAL case, where things appear to be moving in 3 dimensions very, very rapidly in a way that, if it was accurate, would actually be anomalous. So that's what we're looking for in a UAP investigation, anomalous behavior. And to do that, we use line of sight. And line of sight we get from video and from photos. A photo only has one line of sight. You can see in my little example here with me down in the corner, looking up at a UAP in the sight that's just in the sky. There's only one line of sight. And this is, but a video would have thousands of lines of sight, because each frame of the video has its own individual line from your camera to the UAP. This is all fairly basic stuff, but I want to make sure everyone knows what we're talking about. There's 3 ways you can specify a line of sight. There's probably more, but they all boil down to essentially the same thing. I'm not going to get into too much technical detail with this, but you'll notice that each of these 3 ways all starts with a camera position. Camera position, obviously, is the position of the camera in the world. Is what is its location on a map and how high is it? For analysis, we usually want the what we refer to normally nowadays as the GPS position, which is the latitude, the longitude, and the altitude of the camera. And we do sometimes use other coordinate systems. You might see these mentions like ECEF and ENU, Earth-centered, Earth-fixed, and east-north up. But these are things that you use for the actual analysis. The starting point is your latitude, longitude, and altitude. For good analysis of line of sight, you want your coordinates to be as accurate as possible. So you want the degrees, the minutes, and the seconds, and you want, if possible, to have several decimal places. So how do you get a camera position? Well, there's a whole bunch of different ways you can do it. I'll quickly go through all of them here. You can use the EXIF data. Cameras often have latitude and longitude recorded in the image itself, in the photo or in the video. Although with videos, normally all you'll get in a video is just the position of the start of the camera. Sometimes you don't even get that with planes. Sometimes you just get the, you get recorded where the camera just happened to latch onto a GPS signal. Sometimes you get your GPS coordinates on screen. This is a wonderful thing when it actually happens. You can actually see on every single frame of the video, there is a GPS coordinates here. Here's latitude and longitude for the aircraft, and there's also the altitude. And this is for every single frame, so it's a wonderful resource if it's something you actually have on the video. If you don't have that, then you can use geolocation. And geolocation basically means taking any and all information you have about the video and what you can see visually in the video, and then using that to track down the camera location manually. Like in this example here, this was a video of a missile test, and we knew that it was in Southern California because of that's where they're testing the missile. And we knew we could see from looking at the video that it was flying over an island, and it wasn't that hard to just look at all the islands in the vicinity, track down which one it was. This one ended up being San Clemente. Then this is Google Earth on the right here. And what you do in Google Earth is you move around the camera until you get something that matches. This isn't an exact match here. You see it's slightly off, but it's, it's a good start. We would adjust this a little bit more until we've got a perfect match for the camera, and what we see matches. And that gives us a very precise camera location just from geolocation and no other data. Now, geolocation is the ultimate arbiter of location. If your reconstruction is not matching what you see in the original photo or video, then it's wrong. So it's a good idea to geolocate as well, even if you have data from the video itself. Sometimes UAP are videoed from planes, or photos are taken from planes. And if you can figure out the flight number and the date, you can download the ADS-B data, which is the track of the actual location. And then you can either use the exact time from the EXIF data, or you can geolocate the position simply by looking out the window. Often there are distinctive patterns of fields, roads, and mountains. And you can use this to find the exact location. This is something that comes up quite a bit. Sometimes you don't have a location, and you're probably not going to find out the location. This is the GoFast video here, and we knew it was somewhere off the coast of Florida, and we knew its altitude. So what we do in lieu of having the location, which isn't really that important because it's just out over the ocean, is we just pick an arbitrary location as a start point in that general area, and then we just go from there. The subsequent points are going to be relative to that, and they're going to be a high accuracy relative. And we have the altitude as well, so it works out. So the three ways that we have of specifying a line of sight, I'll start with camera position, but then there are additional things which tell you what direction you're looking in. And I'll look at the first two of those here. The first one, position and direction. Position and direction means you don't know a specific point that the camera is pointing at. You just know what direction it's pointing at. And here, this is specified by azimuth and elevation. The top number here, 49 degrees left, is the azimuth, and the number on the left, minus 28 degrees, is the elevation, which is just how much you're looking up or down in this case. Sometimes the azimuth is relative to north, so it's how far north or east or west from north you are. Sometimes it's relative to the position of the plane. So it's actually will vary as the plane actually turns. So you need to know which one you're thinking about. This isn't very accurate. This is only 1 degree of accuracy. So we don't have any minutes or seconds or decimal places. And to use it in a simulation, you're probably going to want to interpolate between these various positions, because at 10 miles away, half a degree of error is going to give you an error of 500 feet in position. So because we don't have that accuracy, you really need to interpolate, apply smoothing. Position and target is where you know the camera position and you know what you're looking at. And you could know what you're looking at from a number of ways. Some videos give an on-screen display of both the camera position and the target position. And in this example here, which is from the infamous rubber duck UAP video, we have a camera position over here, which is the position of the plane, latitude, longitude, and altitude. And we also have over in the top right corner a target position, which gives you a latitude and a longitude, and I believe also an elevation. This isn't necessarily the object. This is actually the coordinates, supposedly, of the ground underneath this crosshair. So it should be this point on the map right here. What we're actually interested in terms of UAPs, is the object itself, which is over here, which we could find out relative to this. But when you actually look into it, you find that these coordinates here are typically not very accurate. They're often not exactly what we're looking at. So you really got to use geolocation in addition to these coordinates. And if you look at what we have behind this, you'll see that the true position of the object is right here. Now, the crosshairs were over here. If we just go back, you see these crosshairs are over here. But these numbers over here refer to something that is about 200 feet over in this direction. So if we were to kind of use the crosshairs as a relative position for our true position, we'd end up way over here. So you've really got to use geolocation in addition to target GPS coordinates. So what do we do with line of sight in UAP investigations? Well, our goal in UAP investigations is to find if something is anomalous, unambiguously anomalous, meaning that it's something we can't identify by conventional means. When we have a video, we want to try to use all the frames in the video. We don't want to just pick a couple of frames and analyze those frames. We've got every single frame. We want to use as much of it as possible. Step 1 in this process is to extract the line of sight. Step 2 is to reconstruct the potential traversals. For any set of lines of sight, there's multiple ways of going across that set of possible line of sight. You want to find the ones that make the most sense. Then step 3 is to visualize and explore the potential solutions in the competing hypotheses. Step 4 is to check against all available information. Step 5, don't eliminate anything, just move it down the list. This is kind of a pet topic of mine. Anyway, so example number 1, this is a video from a webcam in Hale Beach, St. Ives, California. It's showing a light moving across the horizon right here. And then that light, a little bit later in the video, shoots up into the sky. You can see it shooting up there. So this seems like a very impressive video. But the question here is it near or is it far away? Is it actually close to the horizon? If it's close to the horizon, then it's an amazing unidentified flying object. If it's something closer, then it's a bit more mundane. So how can we actually figure this out? Now, somebody did a simple analysis by taking 2 simple measurements from the video and saying, using this person's height in the corner, then using that to try to determine how fast it was moving. And it's, it kind of works. It gives you some ballpark figures, but we can probably do better than this. So step 1 here was to locate the position of the camera, and we know roughly where it is. We can geolocate it. We can find the position in Google Earth. We can set the camera to that position. We can check that the field of view is correct. And here I've set up a camera that matches that particular video. We've got a 45-degree vertical field of view. Then we want to extract the lines of sight, and we can do that in an automated way. We can use Adobe After Effects to do motion tracking of the point, and then we can extract the per frame X and Y coordinates, and that then gives us the lines of sight. We can then apply that. And I'm going to do a quick demonstration of what that actually looks like once we put it into my software. Now, this is a tool I wrote. It's called SITREC, which is short for Situation Recreation. And it's basically the top right here is the actual original video. The bottom right here is the simulation. And this is a 3D view of the world showing all of the lines of sight. And we can skip through the video and we can see the object moving around along these lines of sight. And this top graph here shows the speed of the object in this particular setup. And we can explore the various scenarios by changing the start distance of the object. We can move it further away, and we will see that, when it's way over there, when it's like, I think that's about a mile away, it's now moving at about 100 miles per hour, and it zooms upwards also at about 100 miles an hour. So we can see it very quickly becomes much more impressive as it gets further away. But as it gets closer, we can see that it slows down. And as it gets really close, we can see that it will actually get much bigger in size. So we want to have something that matches the actual video itself and see what the possible solutions are. And it turns out that a very reasonable solution for this particular case is something that's drone sized just over the beach. So does this disprove anomalous behavior? Well, no. I mean, the existence of a mundane explanation doesn't disprove it. It could well be something that's far away, but a mundane solution exists. And I think whenever a mundane solution actually exists, it kind of gravitates towards the top of the list. And we've got to look at the other data that's around this case, like, do other people fly drones there at sunset? Turns out, yes, they do. It's a very popular place for flying drones. So example 2, Aguadilla. Aguadilla was a US Coast Guard, I believe, video filmed in 2013 in Puerto Rico. It's a thermal camera. We're looking at infrared footage showing hot and cold things. Black things here are hot. It's taken at night. There's an object here that's moving along. It has hot and cooler regions. You can see the cooler regions when the background is there. Sometimes you can't see them. Sometimes it vanishes entirely when there's water behind it. And some people have interpreted this as being a transmedium object going underwater. Excuse me. There's 2 main hypotheses to explain this video. Hypothesis 1 is that it is some kind of anomalous object, a fast object close to the ground, circling the airport at over 100 miles per hour, going behind trees, descending to the water, traveling underwater without a proportionate splash or any slowdown at 50 miles per hour, re-emerging, splitting into 2. Hypothesis 2 is that it's a pair of connected wedding lanterns drifting in the wind over the airport. The apparent motion is mostly from parallax. They don't go behind anything. They vanish when the heat source is not visible and the background is similar in temperature. And there's also other hypotheses like balloons and things like that. But these are the main 2 hypotheses. Just to be real clear what a wedding lantern is, it's also called a Chinese lantern or a sky lantern. It's a small hot air powered paper balloon with a small flame at the base. And as it moves around, sometimes the flame is hidden, and in thermal camera footage, the flame will be black and the canopy would be gray. Now, we've got a lot of data. We've got a lot of data in this video. We've got camera position, we've got the target position, and we have a very detailed background here, so we can do very accurate geolocation. It's a wonderful video for extracting data from. But there's 7,000 frames. There's over 7,000 frames of data, and it's a lot of work to get in and extract all of that. So how do we do it? Well, turns out somebody already did. This was a monumental effort organized on the Above Top Secret forum by Isaac Coy back in 2015. And they crowdsourced the extraction of the data and created this 7,000 plus line spreadsheet of all the coordinates. It's a wonderful, wonderful thing. The big issue with this data is that, like most data, it's very noisy. Here we see the 2 tracks that are of relevance. The green track is the track of the airplane flying around the airport. The red track is the ground track, and it's also very, very noisy. Oops, excuse me. That's wrong slide. Okay, so we have to denoise it. We have to smooth it out. We have to get into something usable. This here is the data from the camera position. The white dots here are the positions of the plane, essentially the positions of the camera. And you can, I won't get into technical detail, but basically all I did was create a path that was a physically plausible path through these white dots. So it moves at the same speed and in the same direction as if it was the plane, but it gives us a lovely smooth path from which we can do a recreation of this video. Now, the target track, unfortunately, is very noisy. You look at it there, it's just going all over the place. It doesn't actually have a good correlation with what we actually see in the video. And so it's not really that usable, and you can't even really smooth it out and get anything useful out of it. So what I did was I started with that track and used that as a rough location. And then I created a 3D spline, an edited curved path that went through the general area. I then looked at that path from the camera position, which I have down here in the bottom right with my simulation, and compare that against what we see in the actual video in the top right here. And then I edited the path with these little widgets here until I've got something that was essentially a perfect match. We see the object moving, and this doesn't create a path of the object. This is just creating the lines of sight. We don't actually know where the object is. But it gives us the exact same lines of sight to the object as in the original video. And when we have that lines of sight, then we can start to look at our various hypotheses and see whether they are actually plausible or not. So hypothesis 1, this is what I came up with, was the anomaly. The green line here is a track that matches the hypothesis 1, an object at about treetop height, moving in a circle off the cliff at the end, down to the water and out to the sea. The graph at the top shows the velocity. It's a bit noisy, but it's not too important. That's just an artifact of the spline joining together. And really, the first 2/3 of it are very accurate because that's the only place where we see features we can identify and geolocate and line things up properly. The rest is over the water. And hypothesis 2 is this green line in the middle here, which is a more or less straight line. It's moving from this point here down to over here. And we see on the top, we have a velocity, which starts, I believe it's around 18 miles per hour, and then it moves down to something lower. And the line itself is actually descending. And this so the reduction in speed corresponds to a reduction in altitude. And perhaps not coincidentally, it also is an exact match for the weather that day. And I can do a quick demonstration of what we have there for Aguadilla. We have the full recreation here, and we can see that the green line here is more or less straight, especially at the start when we have good data, and it gradually descends towards the end. And we can see that everything kind of matches with the video in the background. You see it crosses the runway there, and later on we see it crossing the street at exactly the same time. It's an exact match, and I won't get into the tools because I don't really have much time here, but there's a very sophisticated set of things that we can use for kind of editing paths and things like that to move things around. But let me go back to here. And so we've got two competing hypotheses that we've been able to explore with this tool. Can we pick one over the other? Now, it would seem like the lantern hypothesis better satisfies Occam's razor. It's something that's known to happen. This photo here on the right is of lanterns being released at night, and it was actually taken from a hotel that was just upwind of the airport. Basically, if you trace this path backwards in this direction, you come to this location on the beach, and the wind is blowing in this direction. We also have video of a similar event. This is a video taken in Aguadilla on the same year, a few months later, and it shows a couple of what look like wedding lanterns, sky lanterns, Chinese lanterns, drifting across the island from, excuse me, east to west in exactly the same way as was being hypothesized for hypothesis 2. So there's a bit of supporting evidence there, kind of circumstantial. It's a complicated event. I don't have much time here, but very quickly going over the objections. The one objection is that there's always a slow solution to line of sight traversal. That's not really true. There isn't always a slow solution with constant speed in a straight line. An objection is that it goes behind trees and underwater, and that's kind of up in the air. It's not really necessarily true. We also see areas in the video where the object appears to vanish when it's demonstrably in midair, especially when it goes off the cliff towards the end and before it gets down to the water. There's a position where it's not behind any trees and it disappears, similar to when it's over the water. 18 miles per hour is too windy. Well, it's not 18 miles per hour where it's released. It's 18 miles per hour at the upper altitude. And also you can see it wobbling around as if it is fairly windy. Why does it split in two? Well, the hypothesis that there's two lanterns. These are valid and interesting objections, but they don't necessarily disqualify it. I did a quick experiment, which is kind of fun. I created a pseudo lantern in my garage out of paper and a candle, and you can see that the paper of the lantern would obscure a heat source. You'll see when I move up, this little black dot here disappears behind the paper, which is what I'm hypothesizing as the invisibility scenario. SCU did a bunch of analysis of this case. They did a very detailed document. They have an Appendix L where they do line of sight analysis. And they concluded that this line of sight analysis eliminates a lantern or balloon hypothesis. And in their analysis, they assume the same wind. They find a couple of frames with no background motion. And then they claim that this means that only the object is moving. So they use this to calculate a distance to the object, and then subsequent calculations show that a wind speed object is actually impossible. Unfortunately, their assumption falls over because planes don't stop in midair. So the camera is still moving. So there's still a significant contribution of parallax to these two frames, which means that all of the subsequent calculations that they make in Appendix L are wrong. And really that appendix should be removed or revised. They do another line of sight analysis, which they say claims that it couldn't be accurate, but they're using 3 lines of sight here, where it's very easy to make mistakes with a limited number of lines of sight. For example, they also did a line of sight to this tanker here, but they picked the wrong tanker. They picked one that was 500 feet away from where it actually was, which is quite a significant error if you're using that for a line of sight. Mistake like this are very easy to make. This isn't Mick West versus the SCU, though. I'm not trying to be like, me versus them. Lots of people have actually looked at this case and have done line of sight analysis. Here's a few of them. There's the Puerto Rico Research Group, which is a Facebook group. Lance Moody and Florent Michaud did this very nice 3D simulation, similar to mine. Shows the same type of thing, something moving slowly over the airport. Flarkey, an engineer from the UK, did a very detailed analysis. He also sided with the lantern hypothesis. You can see down on his presentation here. John Nagel, SCU contributor, says he felt confident that the object was a lantern balloon. He did a simple analysis, similar type of thing. Bob Bixler was asked by SCU to do an analysis, and he did one. That's not Bob, because that's 3FA. 3FA, the French Aeronautics and Astronomy Association, did a very detailed analysis. This is very impressive. Very similar simulations. They didn't really smooth out the data, so the end result was rather noisy, but they thought that the Chinese lantern, which they call the Thai lantern, was possible. And Bob Blixler was asked to look into this, and he published a report in Sunlight magazine saying that the balloon hypothesis, similar to the lantern hypothesis, was also likely. Ruben Lianza, the head of the Argentinian Air Force Aerospace Phenomena Research Committee, was one of the first people to conclude it was a pair of wedding lanterns. So in summary, with more data points, the better. With lines of sight, you want to use as many data points as possible. If you just use a handful of data points, it's kind of prone to error. If you use lots of data points, then things will leap out to you. If things are wrong, things will jump from one position to another, and you can do a much more sophisticated analysis and reconstruction. Often the data is noisy. You need to smooth it out. You don't want to use the raw data. You need to convert it into something that is both accurate and physically plausible. Like a plane is not going to fly around in a zigzag pattern. It's going to fly in a smooth curve. You need to understand the errors in the noisy data. The ground track can be off by several hundred feet, so you don't want to use that even when it's smooth. You need to geolocate. If you just sample a few points, that can give very misleading results because you're just picking points from noisy data. And it could be somewhere up here, it could be somewhere down there, when really what's happening is in the middle. Recreating a video is a key validation of the simulation or even of analysis in general. If you do an analysis of something using lines of sight and then you recreate a video and it doesn't look like the original video, then obviously it's wrong. If you recreate the video and it looks like the original video, then it's a plausible solution. With Aguadilla, we can't prove it's not a fast transmedium anomaly, but that's a pretty extraordinary claim that it is going underwater and it's doing these other things. And I feel the supporting evidence really isn't there. I'm sure we'll hear more about that later. But from my analysis, a waiting lantern, and from other people's analyses, a waiting lantern seems like the best fit. And I think this type of analysis and the analysis done by 3A and other people, 3FA, shows that software is very useful and can save a very large amount of time. And the problem is that UAP research is kind of a unique use case. You can't use existing tools. We have to create our own tools. So we really want to encourage more coders, people with coding experience, and especially with 3D graphics experience and 3D analysis experience to participate in this. If you want to look at this, there is these tools are actually web-based. You can just go to this link, metabunk.org/sitrec, and you'll be able to play with it yourself. I also have a video viewer that you can use to look at the videos in more depth, and these are the links there. And I'd like to thank you very much for giving me this opportunity to talk, and I'm open to questions.
Thank you, Mr. West. Very fascinating.
Thank you.
Thank you very much. Very detailed. We really appreciate the level of detail here. So we had a sudden change in your assigned discussant. Massimo Teodorani cannot establish a stable internet connection from Italy. So I have asked Professor Kevin Knuth to be your discussant. So okay. I will turn it over to Kevin, who will make some comments or ask you some questions, and then we'll turn it over to the rest. So Kevin, Professor Knuth.
All right, thank you very much, Mick, for this very interesting presentation. Let's see, I'll start with a question. I'm curious. I take your point about the question as to whether these objects are going underwater or not, or this object goes underwater. I use that as an example in my upcoming talk, and so I'm of course very interested in this. And you make a good point that the object also disappears in midair, and certainly it does. So however, do we know why the object's disappearing in midair, and do we know why the object would be disappearing over water? The water presumably is going to be cooler than the land surface. And so I would imagine that there'd be actually more contrast between the heat of the lantern and the background of the water surface. So to me, it doesn't quite make sense that it would necessarily disappear as it's over water. Can you comment on that?
Yeah, I think if you look at the video in the earlier parts of it, you see that the object is made up of two regions, a hot region and a cold region. And I think the hot region is fairly hot, like a flame, or something like it's obviously not a jet exhaust, but something that's hot. And then the rest of it is fairly like ambient temperature. And I think one of the best places to look at in this video is where it crosses over the road. And we see where it crosses over the road, there's a number of cars and other vehicles, and you see the object itself, and you see they look remarkably similar. We see a gray kind of warmish ambient temperature object, and then we see the black of the heat source. And it's not too different from other objects in the scene. So I think the kind of the ambient temperature of the hypothetical lantern is similar to the ambient temperature of these cars, and it's very easy for it to blend in with the background. And I don't know what the temperature of the the ocean was, but this was filmed at night, so presumably the air would be fairly cool, which would cool down the temperature of the surface of the lantern. So the temperature of the surface of the lantern will be, perhaps closer to the temperature of the air than the water. So I think the temperature differential will be fairly small. You see, when it's flying over the water, you can really only see the heat source, which means that the canopy has already disappeared when it's just flying over. All we're seeing is black when it's flying over the water, until it goes, underwater theoretically, and then we can just make out this grayness, which I would say would be the canopy of this hot air balloon. So I think what's happening is that the heat source is just simply being occluded by the balloon turning away. So the heat source is hidden by the mass of the balloon. And so we just see this kind of ambient thing, like we would see one of these cars on the road if someone had covered up the heat source of the exhaust or the engine.
All right, interesting. All right, thank you. Yes, a lot to think about, and of course we'll have to see Robert Powell's upcoming talk as well and see what their how they describe this. But this really points out this makes an important point, that these analysis of data, especially from just one sensor, is extremely difficult. There's a lot of complexity. There's a lot of inference that needs to be made, and this is another reason for having multiple instruments, which is why, we at UAPX and the Galileo project and others are trying to do that. So Robert asked a question in the chat where he asks, and you may have had this in your plot. I thought that you had put up a graph that showed speeds, but he asks, what speed did your model show the object was moving as it traveled east to west? And do you have any evidence that a lantern can survive winds at those speeds?
It starts out at about 18 miles per hour, and I have that on the graph. The graph was a little small, but I had to make it big so I could see the anomalous version. And it decreases as the object decreases. And I don't think 18 miles per hour at altitude is an unreasonable speed. We know that as it gets lower, the speed decreases quite a bit. Now, obviously, if it was 18 miles per hour on the ground, that would be a silly windy day for you to release a lantern at. You're not going to be flying lanterns when it's 18 miles per hour on the ground. But it wasn't. It was a more reasonable, I think less than 10 miles per hour. So the lantern would have been released on the beach some miles away in a lower wind speed, and then ascended to altitude where it's faster. And the effect of wind is relative. So if you're holding something in fast wind, then that's an issue. But if something is moving in fast wind, then it's less of an issue. And especially at altitude, where the air mass flows in a more laminar way, a smoother way than it does at the ground, where it's a lot more turbulent. So this is something that I think, like with the first question, is the ultimate arbiter of that would be a physical reconstruction, and that's something I would certainly like to see done. Physical reconstruction of experimenting with wind speed and various altitudes, but I don't personally think that it's implausible, especially as we start out at a lower wind speed.
Right.
Of course, real quick there. Can I just make one more point there?
Sure.
The really interesting thing about that particular speed and direction is that is the wind speed and direction on that day. We knew that the wind above 400 feet was around, I think, 12 to 18 miles per hour, and at lower level it was around 10 miles per hour, and in that direction, which is the path that emerged from the analysis. It wasn't me trying to force that path. That was really the only plausible path, was one that actually matched the wind speed.
Right, and let's see, I just happened to notice Rich Hoffman had something related to that. Where,
actually, there's a hand up from Professor Sadagis. Maybe he could throw in.
Right. Yeah, I'm having trouble seeing the hands up, so if you can help me with that, that'd be great. Yeah, Matthew, you can go.
Thank you, Kevin. Mick, that was a very good presentation. I'm curious, obviously, what Robert will have in his, but on the face of it, definitely find what you have is very compelling there. But my question is more of a big picture, general one, since you mentioned, of course, Occam's razor several times, and I wanted to ask, what is your opinion, though, of the perspective that, at least in science, from the history of science, and speaking from myself as a particle physicist, one possible perspective is actually the history of science is, from one point of view at least, a scathing indictment of Occam's razor, since, for example, earth, air, fire, and water, and ether, the Greek 5 elements, that's way simpler than the periodic table of the elements or the standard model of particle physics, which is really, really hard and really complicated. And similarly, Daniel Kuhn mentioned earlier, Newton and Einstein, general relativity is extremely hard. It's a graduate level course. Newton can be taught to first year undergraduate students. So the history of physics seems to show that Occam's razor is a cute idea that works a lot of the time, but doesn't really seem to work and when you actually put that principle under the microscope in the hard sciences. So I'd like to hear your thoughts on that.
Sure. Well, Occam's razor is kind of a rule of thumb. It's something that's very useful for kind of making initial determinations of hypotheses. And if you don't have anything else to go by, it's a very good thing. And it isn't really like which is the simplest explanation. Because if you look at these two explanations, in some ways, the simplest explanation is that it's an anomalous craft. We can just say, oh, it's just some kind of advanced technology craft, perhaps a non-human intelligence-powered craft. And we don't have to explain beyond that. But Occam's razor in its actual original form isn't the simplest explanation is the best. It's the do not multiply entities unnecessarily. Do not add things to the explanation that are new. And here we've got two explanations, one of which is just wedding lanterns, which we know exist in that location and match all the available data. And the other one is some mysterious anomalous craft. So we're introducing something new, and not just something trivial and new, like a new type of drone or something like that. We're introducing something that seems to defy the laws of physics in the way it dives underwater. So there's a very significant difference, which I think really Occam's razor does speak to, in that the lantern hypothesis doesn't bring anything new. The anomaly hypothesis brings something incredible and amazing and new. And there's a very big distinction. And since that's our pivoting point, I think we have to go towards the simpler explanation in an Occam style.
Kevin, can we have an intervention here from my colleague Michael Superstein, philosopher of physics here? We just want
Certainly.
So Nick, great talk. I thought it was really interesting. I have nothing to say. I have nothing to say about this particular case, and I have no idea how to adjudicate it. But the sort of conversations you guys are having about this, I think, is very important, and it's the sort of thing that we ought to be doing. So I do want to do a little big picture scientific explanation thing. Now, I'm not going to talk about Occam's razor because, yeah, it's a value judgment, whatever. It's not always the simplest thing. How do you define simple? But let's just make it more bare bones. So I think I hope everyone, well, at least everyone who wants to play the game of science, agrees that we want to figure out whether or not the black swan is more probable than not than what you call the mundane scenario, and that's fine. But we just want to make sure that we're all our Bayesian priors are the same. We want to make sure we're all agreeing on how we're going to adjudicate when we place these bets. We can't be using different epistemic criteria or what have you, right? So in the case at hand, which of these is more probable? Well, it's going to come down to an awful lot of questions, right, about the physics of balloons and the thermodynamics and all kinds of things, which would take again getting out of the details. But one of the things I do want to say is, in a lot of these cases, there are multiple, this was Daniel's point, there are multiple streams of convergent evidence, right? And I don't think we can go through each case and do what you're doing, and we should. But I think we have to take all those different streams of convergent evidence and all the different cases together when we decide, which hypothesis is more probable than not. So I guess my question to you is, do you think that when you look at the preponderance of evidence that these people who were speaking yesterday, it's absolutely reasonable them for ask and to receive funding to try to acquire more data? Would you support that?
Sure. I mean, I think, you talk about getting a common epistemic framework, but I think that we're kind of hobbled here by the fact that we're all individual people and we're all working independently, and we're not just all in the same room together working on the same thing. So we're naturally going to have lots of divergence within that. But yeah, I don't see any issue with people asking for funding to study things. Like if there are unidentified objects in the sky, then it would be good to identify them. And if there are mysteries floating around in the sky, it would be good to try to solve those mysteries and to figure out what we can learn from them. But if you want to do that based on good evidence, and you want to do it based on cases that do actually stand up to analysis, and as you kind of pointed out, we do have a wide variety there, and I think you do at some point have to look at individual cases and see whether they hold up. But I have no objection to a broader study of this topic.
I think we should look at every individual case and see if it holds up. I agree with you. We have to consider all the streams of evidence in each of those individual cases. And to your point about a common epistemic framework is an idealization to achieve, but it is what drives science, right? So the whole idea is to have, so when we assign sig figs and we place bets about, the nature of black holes or whether or not psi exists or what have you, we at least presuppose, right, that we've agreed on what, is going to count as who's going to win, who's going to lose under what conditions based on what procedures. So that's all I'm trying to do is, in effect, get everybody in the same room and agree on that so that nobody's cheating, etc. Does that seem?
Sounds reasonable, yes, but I think it is perhaps a bit overambitious because the rest of science really hasn't got there yet. And we can use the rest of science as a basic framework. What are the levels of evidence that we need? But even in other disciplines that are older and more well established, there's still a variety of approaches and a variety of people. So I think we're probably going to be stuck with that for some time, but it's certainly something we can work towards improving.
Thank you, Mick.
Thanks. I think unfortunately we're going to have to transition over to the next. So Kevin, if you could also be the discussant for Robert.
Yeah, that would be fine. I think I would just like to finish by adding that your trajectory is a straight line over the airport, which I think is in some ways, if we're going to talk about simplicity and Occam's razor, is a very simple solution, right? And the fact that this straight line motion is something you would expect from something like a lantern is compelling. But then I also have to ask, why is it, if there's a hotel downwind that regularly releases Chinese lanterns, then why are the personnel at the airport interested and surprised and bothered by Chinese lanterns flying over the airport? Why is this a mystery to them? And so there's a lot to think about here. And
I
again,
don't know.
these problems aren't simple.
I don't know, but we do know that it's something that does happen, and it was perhaps not that familiar to the people who were on duty that night, and they saw something that they didn't immediately recognize. I mean, it might not be something that happens every single day.
And misidentifications
we don't know.
that happen all the time. So,
it's it's another thing that kind of like modifies the hypothesis in terms of plausibility, but I don't think it's something that eliminates it, especially as we're considering far more exotic explanations as well. So the fact that someone might not immediately recognize a waiting lantern isn't really as exotic as something that travels at 50 miles per hour underwater.
Right. Thank you so much for your talk. I really appreciate it. And
thank you, everyone.
Thank you very much, Mick.